This video is about covalent bonding. When atoms share electrons, they form a covalent bond, and these are really strong bonds. And covalent bonds can occur in simple covalent molecules and they can also occur in very large structures called macromolecules that form giant structures. But in both cases they involve the sharing of electrons, and really importantly they exist between non-metals. Okay, so it's bonding between non-metals. And if you remember on the periodic table, you can separate the metals and non-metals by the zigzag line on the right hand side, which exists between boron and aluminium, and everything on the left hand side is a metal, everything on the right hand side of that zigzag line is a non-metal. So if you see two things from the right hand side bonding together, that means that they are forming a covalent bond and sharing electron. So some examples of simple molecules that we need to know about are things like H2, O2, Cl2, HCl, H2O, NH3, which is ammonia, and CH4, which is methane. We need to be able to draw these and recognise these as covalent molecules. For the macromolecules, which we'll discuss in more detail in a later video, you get things such as diamond, graphite, and silicon dioxide. Silicon dioxide being the covalent bonding between silicon and oxygen, and diamond and graphite are quite simply both different structures which are made out of carbon. So carbon bonding with carbon is again a covalent bond because carbon is a non-metal. So how we draw these covalent bonds is very different to how we drew the ions. So ions, when we looked at those, were existing as charged particles in brackets with their opposite charges attracting each other. This is totally different to how we are going to draw the covalent molecules. When drawing covalent molecules, you only draw the outer shell of electrons. So I'll just put that up there to remind you. So draw the outer shell of electrons only. So for example, to take the most simple one, H2, number 2 tells you that there's two hydrogen atoms bonding together. So hydrogen atoms themselves have only one electron in its shell, and it only has one shell. So two hydrogen atoms bonded together, I'm going to draw one as a circle to help us and one as a cross, would look a little bit something like this. So now we have two hydrogen atoms together, but they are sharing a pair of electrons. So one hydrogen atom has got this electron, the other has got this electron, but together they are sharing it. And in the case of hydrogen, it has a complete outer shell because hydrogen only has one shell, and that shell can only hold two electrons. For a second example, if you take chlorine, this will be bonded to another chlorine because it's Cl2, and they will share a pair of electrons, and each of them has 7 in its outer shell because chlorine is in group 7. But because they are sharing that pair of electrons together, they have 8. So this chlorine, 1, 2, 3, 4, 5, 6, 7, 8. And if you were to look at this chlorine, 1, 2, 3, 4, 5, 6, 7, 8. So in each case they want a full outer shell, but they gain their full outer shell by sharing electrons as opposed to giving or taking electrons. So molecules that go around in pairs like this as well are called diatomic molecules, so di meaning 2 and atoms, diatomic molecules, and there's lots of examples of covalent molecules that are diatomic. So withdrawing oxygen, oxygen is O2, so we have 2 oxygen atoms going around together, and the easiest way to draw it is by first drawing in the circles for the atoms, and then thinking about how many pairs they need to share. And the rule is, if they need 1 electron in their outer shell to complete their outer shell, they need to share 1 pair, and if they need 2 electrons in their outer shell to complete their shell, they need to share 2 pairs. So I'll draw one of the oxygen atom's electrons in blue. So the oxygen atom needs 2 electrons because it's in group 6. It would need 2 electrons in its outer shell to complete its outer shell. So if I draw these ones in first, it sometimes helps. So this shows that there are 2 pairs of electrons being shared, and we need to fill in the extra electrons on the outer shell of the oxygen. So oxygen has 6 on its outer shell, we've used 2 there, 1, 2, 3, 4, 5, 6. And the same for this oxygen atom, we've used 2, so we need 3, 4, 5, 6. So in this case, oxygen needed 2 electrons to complete its outer shell, so it needs to make 2 pairs of electrons, which you show them sharing by the electron shells touching there. This is slightly different from hydrogen, because hydrogen we drew, and hydrogen had just 1 pair of sharing electrons, so we would draw hydrogen in a different way, like this. This single line here represents a single bond because they're sharing a single pair. Whereas oxygen, this has got 2 shared pairs of electrons, so we would say that this has a double bond, and we'd represent oxygen like this with a double bond. In fact, there are 3 ways in which you need to be able to represent covalent bonds, and I'll use the example of ammonia, which is NH3, to help explain these 3 different ways. So the first one we've already looked at before is where we have the rings to show the different atoms. This being nitrogen with 3 hydrogens, as the compound formula suggests. We'd use a circle for the electrons of hydrogen, and we'd use a cross for the electrons of nitrogen. Nitrogen is in group 5, so it has 5 electrons in its outer shell, represented by the 5 crosses. 1, 2, 3, 4, 5. Hydrogen has one electron in its outer shell, represented by the circles. So each hydrogen atom has one electron, but when bonded together, the nitrogen now has 1, 2, 3, 4, 5, 6, 7, 8 electrons and a complete outer shell, and the hydrogens now have 1, 2 electrons and a complete outer shell. The other way we can draw this is by not including the rings in, so you might see it represented like this, where you have the nitrogen and the hydrogens, but you don't have the rings written in, so you need to recognise that that is the covalent bond as well. And the third way is what we're alluding to up here with the bonding, whereby you might just see a covalent bond as a single straight line between two non-metals. So if it was oxygen, for example, you'd see two straight lines because that's a double bond, but here in ammonia, NH3, you only have single bonds because there's a single shared pair of electrons. So I'll do one more example with H2O. So we know we need two H's and one oxygen. So we've got the oxygen here and the H's for hydrogen. Now you know that hydrogen needs one electron more in its outer shell to be complete, and oxygen needs two. So by sharing a pair of electrons here and a pair of electrons here, you should have a complete outer shell. So for hydrogen, you'll be sharing a pair of electrons with oxygen, and oxygen, if we use the crosses for oxygen, we've already used two here, which means we need to draw four more because oxygen has 6 electrons in its outer shell, 1, 2, 3, 4, 5, 6, which when combined makes a complete outer shell of 8 electrons. Without the rings we could draw it again, just with the electrons. Show oxygen and the hydrogens, and finally if we were to draw it just by our lines representing covalent bonds, we could draw water like this. Now have a go at doing the same with methane and hydrogen chloride. Pause the video now. So methane, you've got one carbon molecule with 4 hydrogens. Carbon is in group 4, it has 4 electrons in its outer shell, and that will make one pair with each of the hydrogens to make CH4. We've got hydrogen 4 times around the carbon to make our CH4, and if we draw this in molecule form, this should remind you of the alkanes you were drawing in C1. You've got the non-metal of hydrogen bonded to a non-metal of carbon, therefore this line must represent a single covalent bond. Finally, hydrogen chloride, you would have one hydrogen bonded to one chlorine, and chlorine needs 7 electrons in total, so we've used one there, so I'll put the other 6 in, and with this one that it shares with hydrogen, that would make an outer shell of 8. Without the rings, this is how we draw the diagram, and finally in the simple form with the lines representing a covalent bond, this is how we would draw hydrogen chloride.